So, hello everybody, welcome to another tutorial. Today we will talk, as the title says here quite well, about quantum level molecular visualization with Blender. Yeah. This whole tutorial is basically inspired by an article that I've written in 2015, which is called Visualization of Molecular Properties at the Quantum Mechanical Level using Blender. You'll find it here if you follow this link. I won't go there. You can read this. This is way more detailed, of course, than this tutorial. In this tutorial, I just make a step-by-step guide so that you can do this at home, that you see what molecules really look like, what molecules look like on the quantum mechanical level, what is a different representation than these ball and sticks representations all the time, so that you yourself can render what is called the electron cloud around a molecule, yeah? So that you get the representation which is given by, let's say, by the Schrödinger equation for any type of molecular structure, yeah? So we do this here, and what are we talking about? That's a really fancy introduction here, but the big deal is that most molecular visualization software is geared to what is called this atomistic representation. So you have PyMol, VMD, RASMol, and all these kinds of tools, of course, in order to visualize molecules. But if I come up here with VMD, for instance, let's do this quickly. VMD comes up, I can say I want to have a new molecule, and here you can type a PDB code, you know this very well. I load a PDB molecule, and you see I have this this lines representation here, and of course I can change the representation and say, for instance, van der Waals, where is it? I don't see it. No, it's coloring method. No, van der Waals representation, and you see then in this balls representation. But this is not, of course, electrons, and this is not electron density, and this is not what people who know about quantum mechanics envision what the molecule looks like. Yeah. Probably you have seen these fancy models of hydrogen atom representations about these with these shells where the electrons shall be found. Here we will show you how you can do this for a molecule, how you can represent the electron cloud about the molecule. Yeah, let's not overdo it. It's not that fancy either, but it gives you a more detailed, a different representation of the whole system. Yeah. Okay. So we got this. So let's quit VMD. You see with VMD, in VMD you have this volume options, but these volume options, they are really very slow, very not that nicely implemented. You don't get that nice graphics out of it. We want to do this with Blender, which is a full-blown 3D animation studio tool. Let's say it like this, which is used in the movie in commercial industry in order to make commercials which are 3D animated, like little Pixar-like movies, if you imagine. And we will show you how you can use this tool, how you can leverage this tool in order to visualize your molecules on a quantum mechanical level. Yeah? Okay, enough about the introduction. Yeah? We already overdone it. Let's get to the tools that we use. So we will use Babel, or better Open Babel, in order to convert what we call a Smiles code into a 3D structure. So Smiles code, we will see this later, is just a one-line representation. It's the chemical formula of the molecule. If you know the chemical formula of the molecule, Babel can basically, using internal force field calculation, something like that, create you a 3D structure, a rough approximation of a 3D structure of a molecule. Then we use NWChem. NWChem is a ab initio calculation suite. Crazy story, but it allows you to perform all these quantum mechanical calculations. So ab initio means that you didn't make any chemical experience. You just put, as we do it here, a chemical formula. You have your 3D representation that you build up, and ab initio, so from that, without making any measurements in the real world, you create your electronic structure around the molecule, and see, in our case here, what is the probability to find an electron in a certain point of space around the molecule. Okay, and of course we want to visualize all this stuff, and in order to visualize it, we will use a software which is called Blender. So let's quickly get through this. So Babel, you can all apt-get install this. So here, if you want to install Babel, you do apt-get install open Babel if you're on Ubuntu. Otherwise you use your tool yum or whatever tool your distribution has in order to install this. It's probably in most distributions. In Ubuntu it's in there. All three of them. Blender, you can download it on the website. Most cases this is the best way to do. I won't do it here for this tutorial, but you can download it from there. You just need to have the SDL library somewhere installed in order to get it running if you don't have it. But if you're on a recent desktop, you just download it, put it in some place, double click on Blender where you have downloaded it, and it works. Otherwise you install it with your distribution. Both is possible. That's the way it is. So Babel, open Babel. It's not that interesting. NWChem has a website. You will find it. You just type it in Google and you get through all of this. And Blender, of course, it's blender.org. And this is the software to make these little pixel-like animations. So I won't open my movie here, but you get the idea, so it makes these pixel-like movies, Okay. What is a smiles code? So let's start with the first part here. What is a smiles code? So this is the simplified molecular input line entry system. If it comes up here when I click here, and you see you have a molecule, and you know its representation, and you can write it down as a one-liner here. So you see you have, without these brackets, you have this main chain here of the molecule, and with these little brackets you can create these side parts here, which then can even connect to each other, and that's with these numbers here. And that's the way it works, and that's the way you can represent any type of molecule in this smiles form. And for the tutorial that I show you here, well, we use the smiles form of this caffeine molecule in order to render our caffeine molecule. That's what we want to do. Okay. We did this here. So that's the smiles code. So that's the smiles code for caffeine. So if you type in Google smiles code for caffeine, you will find this. This is the caffeine molecule, this molecule down there. You can probably follow it with the tool that we have seen here. So there's like CN. It looks like we start here, CN1C, something like that, and and we did go over this molecule here. That's the smiles code. That's the caffeine molecule. There are people selling t-shirts with that. If you don't know it, that's what it looks like. And we need a 3D structure. This is a 2D structure. We need a 3D structure from that. And in order to do this, we use open Babel. And with open Babel, we can basically convert this one-liner here into a 3D molecule. So let's do this. So if you don't have open Babel, you just install it on your distribution. As I said, in Ubuntu, for instance, it's in apt-get no stuff. So I will make a little folder here, our tutorial. Let's make it like this. So tutorial. This is an Ubuntu machine. This is not my local machine. I don't have installed all of this of my little laptop, so I do this on this remote machine here. And as I told you, we have here the smiles code. So let's take the smiles code, and we have to create the smiles file. So the smiles file is just one liner with this smiles code. So what I can do in order to create this smiles file is I can do something like that and say, okay, let's pipe this into our caffeine. How is it written? Caffeine? I'm never sure, but into our, let's say coffee. No, it's easier. Coffee.smiles file. Yeah. So if I do this here, you all know this Unix commands probably, so this just writes me this into this file without using an editor, so one line and then enter afterwards, so new line skip, and if I do this, so that's the contents of the file. Yeah? Okay, so I have my smiles file with this one liner here, and right now I can use Open Babel with this code here. So here I named it other caffeine smiles. Yeah, so we do this coffee smiles right now, and we will do this generation here. So I will copy paste this over here, and I will tell you what this is all about. So Babel, of course, is this software suite which compiles me this into, which converts me this into what I need here. Then I have here my coffee. That's it, XYZ file, so this is -O for output, -H. You don't have to forget this -H is very important because this generates hydrogens. Yeah? If you look at the smiles, there are no hydrogens in the smiles. Yeah? And with this -H, it adds all the hydrogens to the structure that we will generate here, yeah? Which we need, of course, for the ab initio calculations. Yeah? Because otherwise we don't have the correct electrons, and of course we don't have any hydrogens, doesn't work. Yeah? And then we do this Gen 3D, and this Gen 3D, it's also needed. It's needed so that in this coffee XYZ with 3D coordinates. If you don't do this, you have just you have the coffee molecule, but without any 3D coordinates. That doesn't really work. Yeah? Okay, so we do this here. And we have here one molecule converted. How cool, huh? And then we have this XYZ file. So let's open this quickly in Emacs here on this remote machine. And we see we have 24 atoms. And here we have all the atoms, and this is like the XYZ coordinate of the atom, and we have a 3D structure. Cool, no? That's what it looks like. That's what we need in order to do our calculation afterwards. Yeah? We can pretty quickly visualize that. I just have to transfer this over here. Need the IP address of that machine to transfer this little coffee molecule here. Tutorial coffee XYZ, and then I can if I don't type my password wrong, with VMD for instance, as these are just the atoms coordinates. So this here, you see, this is a 3D structure of our little molecule. Of course, this is not perfect structure. This is the way how the force field in Open Babel generates this stuff, and we still have to optimize that. That's what we will do with the NWChem suite, and we will calculate, of course, the electron density and the real representation of the molecule with NWChem. Yeah. Okay. So right now I've shown you how with Open Babel you can convert this molecule. Just to remember it, this was the line. This was the how we did this. You need this smiles code. You compile it into an XYZ file. You use -H Gen 3D. You got it. Okay. That's the way it is. Forward to quantum chemistry. So let's talk a bit what we're doing here. So we use what is called the stationary Schrödinger equation. Yeah? And this here is basically the kinetic energy operator, if you want. So this is the momentum squared divided by 2m. The momentum operator in quantum mechanics is something like IH bar nabla, so the derivative into x, y, z coordinates, and here you have IH squared, this the Laplacian or nabla squared divided by 2m applied on what is called this psi. So you could use this in a bracket and put the psi out, and this kinetic term and this potential term without the psi is called the Hamiltonian operator. Yeah, the Hamiltonian of the system. And this psi, so what stands here is basically kinetic energies. So energy and potential, kinetic and potential energy is energy, and this is like an eigenvalue problem with eigenfunctions. Instead of vectors, you have functions here, and you have eigenfunctions. Okay. Of course, you could write this as an infinite matrix if you want to. And then you would have here a vector, and if you use functions, and this is called the wave function. And this wave function is the property that it gives you the probability in space where to find, in our case, an electron. So as I told you, Schrödinger's big idea, or big breakthrough with this equation here, first he wanted to use a different equation. He wanted to use the Klein-Gordon equation. You can look it up, which is here this Quabla operator, which is called, looks like it's different wave operator here, and basically he couldn't solve this, and he used this equation, and his big idea was to solve this as an eigenvalue problem, as I just told you. So H is basically this kinetic term and this potential term. In our case, of course, more complicated than here, because you have to put in here, well, multi-particles and not one particle. So he solved this for the hydrogen atom. So one electron core, one core, and the electron moving around. So for this one electron problem. And if you have multiple electrons, it gets more complicated. You have a multi-particle equation, and you can't solve this anymore analytically. And he was very happy because he could solve this for the hydrogen atom, and he got out the energy states of the quantized energy states of a hydrogen atom, which were verifiable, of course, and known already. And this was the breakthrough of this equation. And we will use an approximation of the Schrödinger equation here in order to get this wave function, and of course this electron density out. So this is then normalized so that this psi square term, psi can be a how do you call this, an imaginary number, and as such you square this out here and you get a real number, and this is the probability, so you can say this here is the probability density to find an electron in space, if we write this down this way. And that's what we will get, and that's what we will visualize. So this is our electron cloud then. And of course we use an approximate solution, so we won't go through all this. This is just a pretty sketch, what's going on. And for people who don't know anything about this, of course you can still use this and have a nice quantum representation and a nice representation of your molecule. And so we use something which is called density functional theory. The density functional theory is a great way of doing this for multi-particle systems with several approximations of this stationary Schrödinger equation. And there is the level of theory, as these theoretical chemists call this, is called P3-lib. So P3-lib is basically the form of the Schrödinger equation, if you want it like that. With this density functional theory, so you have like this functional with this density here. This is called Becker's 3-parameter Li-Yang-Par, I guess, is the authors of this level of theory. This is an exchange correlation stuff a bit complicated to explain here. We won't go into all the details here. Let's see it as an approximation of the Schrödinger equation. Yeah? And this 6331 star is basically the basis function. So the basis function, so this like when you know about Fourier transforms or stuff like this, you have like a basis functions, and you develop this psi in this basis functions here. Yeah. And this is part of the approximation. Yeah? But if you want to know more about this, if you want to know more about this basis function, if you want to know how you get from here to B3 lib, it's summed up in my thesis. Yeah? So you can go here, and I wrote a little review and summary when I worked on all of this, so that people can get started with what I then built on top of that. In chapter 5, page 104 FF of my thesis, you have a nice introduction on how to get from here to B3 lib 631 star. Yeah? Just read it if you're interested in this. We don't have time in a tutorial to have here a real course on quantum mechanics. What you should take away with this is you have the Schrödinger equation with the Schrödinger equation, or with approximations of it. So what is called Hartree-Fock, and then you go to these these equations, and to get to this, and from there you get to density functional theory and exchange correlation, and to this basically to this B3 lib 31 star theory. Yeah? So it's an approximation of the Schrödinger equation, which allows you to calculate this wave function. This wave function gives you the probability. So for r, for a point in space, what is the probability to find an electron there? Yeah, that's how it works. Yeah, take this away. If you want to dive into it, click here or go to this website. You can't click here, of course, in the video, but go there and read it from chapter 5 onwards. Yeah? Okay. So we want to calculate this, and we will use the NWChem software. So we need to write an NWChem input file. Yeah? So we will do this together here. First, we start off with the header. So let's do this here. So let's do this with Emacs here on this remote machine. And we call this our coffee. Let's call it coffee input. NWChem file, something like that. You can call this whatever you want. It's a simple text file. And I copy here the header. Here you can put in a job name. So let's call this the coffee job to stay awake during our tutorial. And we have, this is how much memory I want to give to this job. This is how many iterations I want to do during this electron configuration calculations, all this stuff. We do 100 here is basically fine, probably for all the molecules that if you want to do small molecules like the ones we do here, like this coffee molecule. Yeah. So once we have this header, let's just call this the header. We need our geometry definition, and the geometry definition, well, we have our XYZ file, so we will use our XYZ file in order to do this. So you need to copy this line over here to tell you, of course, in what units your XYZ file is. Here angstroms, yeah, that's what Babel automatically outputs, and this autosym basically tells the NWChem tool that it can rotate the molecule around without changing its internal structure, so that it can do easier its calculation. Okay, not that important. And right now we need to get our XYZ file, so I will open it up here in Emacs in a second window. You can copy paste this with your own editor. You do this the way you want. I have here my coffee XYZ file that I open here, and I can, using Emacs, I can just select all those lines here and copy them over into the other file that we will write out, and just looking at it, if I go here, I skip this 24, which tells us this XYZ file contains 24 atoms. We don't care about this. We just need we just start off here at the first line. That's how NWChem works. Yeah, so we can go back to the other file and we type end here. That's it. Yeah. Okay. Now we have all the atoms. So this is the atom type, which of course is straightforward. Why do you have coffee here? That's sorry for that. There's something wrong here. Yeah, right now I'm in my oh my god, there are so many files open. So this is here the right file. Sorry, because I did this before. So coffee input, just to be sure. We have here the header. I copied the line, I copy pasted this, and at the end you have to write end here, which is very important because of course otherwise it won't run. Yeah, so and after this 3D representation, I copy pasted this XYZ over, and then we have the job properties. Yeah, very easy. As I told you, we use these 631 star bases, so we have to tell it, okay, use these bases. So that's just copy paste over there. Then we do density functional theory with exchange correlation and these piece-related parameters. Yeah, also very easy. Yeah, that's just the theory that we use. If you want to know more about the theory, as I told you, just go into my stuff there, into my thesis. You will get a description of what piece-related is, or just, if you're really advanced, look it up on the internet, piece-related, and you can read the articles whatsoever. So then we want, of course, what we want to have is a cube. So a cube, what do we do here? So we print out a voxel representation of our molecule. So so we have a 3D cube with little voxels in there, and in these voxels we have a value like pixels on a screen, just that it's here in 3D. We have a value, well, what is the electron density in there, and this allows us then to render this in Blender. Yeah, that's the way it works. Yeah, so we need this cube here. We're on a grid. I will write here 5.5. That's far enough for our little molecule here. And this 249 basically tells us that we have 250. Yeah, this is one less. You have to write it that way. That's the way they programmed it, in that way, with this plot tool here. This gives you the electron density in this cube file. Yeah, Gaussian here tells you the cube type. So this comes from the Gaussian software who originally invented this file type. Don't care about this. It's just a way of writing out the data. And here that's the name. So we will call this the coffee cube. No, coffee cube. And that's basically it. Yeah? And then we tell it, well, run this. So task, TFT optimize. So use this density functional theory to optimize my molecule. So what it does here is it minimizes the energy of the molecule so that all the atoms are in optimal position as Babel. Yeah, just did this without quantum mechanics. Yeah? So they guess it with some kind of force field where the atom should be. Yeah, and then plot it. Yeah. Plot it, well, that's just calling this dplot here, and this creates us our cube file. Yeah, that's what we want. Yeah, and that's it. So right now, if you followed my instructions, you have a input file for NWChem in order to calculate the electronic structure of this little coffee molecule. No, so let's close this, and right now you can run this with NWChem coffee input, if I didn't make any mistake. And what I suggest you is that you use this little greater sign here, and to redirect the output of this into an output file, and that it doesn't spoil your terminal. So let's call this the coffee output, coffee NWChem out, because our output actually is the cube file, no? And we run this here, and it runs, and it takes like 15 minutes. And of course I won't do this, I won't spoil you with 15 minutes on this. So this is 15 minutes on a 12 core machine, I guess, something like this. How many cores does my little machine have here? 16, yeah, so it's 12 maybe, yeah. So if you have a faster machine, more cores, something like this, it will run probably a bit faster. That's the way it is. Yeah, it takes about 15 minutes to calculate all these electronic structures for this little molecule here in this level of theory, with the number of atoms that we have, and that's the way it is. So I won't have you waiting 15 minutes, of course. Already pre-calculated the whole stuff. But let's see how far we get. Let's keep this a bit running over there and continue here with transforming the cube file. So transforming the cube file, then we need to transform the cube file into a representation that is readable by Blender. Yeah? And the way it works in the new Blender versions is that in order to create your own volumes, the easiest way right now is, or one of the ways to do this in the old times, yeah, that's why I've written it that way. It was like you had an 8-bit raw file. So 8-bit raw file, it was just like you had all the raw values, so all each byte in bytes in a file basically, and you just told it, okay, this is XYZ, and it created you a volume from these little values from 0 to 255. Yeah? That's nice, but this doesn't work anymore. Yeah? So in the new versions, so you need shaders and stuff like that, and you have a new type of volume rendering. And what we do is we will create an image stack. Yeah? So we will create for each part of the volume slices, let's say like this, and we stack those images on top of each other. And this is then the volume of our molecule. Yeah, that's the way it goes. And in order to get all this running, well, you have here my little website or my little GitHub repository, where if it comes up in the browser, right now we have two browsers, how nice. So here we have all this stuff. Yeah? And we have here this little so all these little tools that we need for that. The binaries in here, so it tells you have binaries with that. Here I should update once the readme and all this kind of stuff. But the binaries, they're outdated, so you have to recompile the tools. Yeah? I will go through with you a few this. So you copy this, and you use your terminal, not this one because that's the remote machine. This one here, and you clone this onto your machine. Yeah, so that's all you need to do. Git clone, and then you have these Quantum Blender visualization tools. Let's call them like this, no? That go with the aforementioned article. Yeah? So we have all these tools, and the tool that we need then is this. The first tool that we need is this cube to raw tool. And the second tool that you need is this raw to image Python script, yeah, in order to create from this 8-bit raw file that we have initially created these little image stacks that I told you about. Yeah? That's the way it works. Okay. So let's compile this. Yeah? So how do you compile a tool like this? You use GCC. If you don't have GCC, you know, on an Ubuntu machine, it's in build essentials. So it's apt-get install build essential, something like this. Then you get GCC and you get all the stuff that you need in order to compile this. I have, of course, on my machine I have this. I'm not on Ubuntu, but I have GCC, of course. So I do O2 for optimize to the second level if you want to. Yeah, the O2 is pretty safe optimization story. MArch, you say native, so then it builds a binary for your processor. Yeah, doesn't use a generic processor that runs everywhere, which is a very old model. It's like this. Which doesn't use all the instructions that in your processor are available. If you use this, it uses all the instructions that in your processor are available. Cube to raw. Okay, C, output cube to raw. We will overwrite the output, which is outdated and which doesn't work anymore, on this machine, and then we link it to the mass library, so LM. Yeah, you need to do this, otherwise it doesn't work. And we compile this here, and we get some warnings. Forget about the warnings, nothing special. This is just, didn't use a return value for some kind of stuff here. It doesn't matter. Implicit declarations, one should fix this more little primitive tools a bit one day, but this of course all works. Don't think too much about it. Okay, we have compiled our tool, the cube to raw tool, and we can convert our cube if it finished. Maybe let's see what's going on here. No, it's still running. So as I told you, this takes some time. So we won't use the new cube, we'll use the old cube. So I already did this. So demo, I guess, or in demo 2, demo. What do we have here? 3D demo, no, something like this. Do I already have a cube here? No cube here. So in demo I have a cube, the caffeine cube. So that's what you get. These are all the output files here. I named it all caffeine. But you get then a cube. When this finished, you get a cube. In our case, the coffee cube. I will just take this cube here that I already pre-calculated with my NWChem file here. Before this demo, which is basically the same output that you will get. Okay, so to speed up this here, so let's copy over our cube from that machine to our place. If you run this, of course, on your machine, you don't have to copy everything over. I have to do this because I don't have NWChem on my little laptop that I used to record this, and I don't have Open Babel also installed on my little laptop. This is my presentation demo laptop. So let's get this here. I need the IP address of this machine here. Okay, SCP demo. What was it? The caffeine cube? No, something like this. I wrote it that way. I never know how to spell caffeine. Okay, something like that. Okay, let's get this copied over here. It's copying, and in this cube we have, well, as I told you already, all the result that we need. That's the story. So we have really here the caffeine structure here, the electron density already calculated just with this NWChem input file that I've shown you before, and by running NWChem. And as I told you, well, it takes a bit of time, 15-30 minutes, something like this, to calculate it for a molecule like this. Okay, so we have this here, and right now we want to create an image stack from that, no? And in order that we can get this into Blender, so we have to transform this, as I told you, no? So I compiled this cube to raw tool in this, that's here, in this Quantum Blender Viz folder. So I will create here a new folder, the coffee folder. Let's move the caffeine cube into the coffee folder and call it coffee cube. Nobody cares, no? And as we have it in there, we can use this little tool, our little tool, in order to create a raw file from that. Yeah. So let's do this. So we have Quantum Blender with, and we have this cube to raw file. And how does this work? So it uses a cube. It writes your output, and you have number of frames. Forget this number of frames, just put one in here. This is basically to get multiple copies in this raw file. This was needed for some Blender stuff that I did with that. Just write one here. Okay, number of frames, one, if you use this tool. This is very artisanal if you want to, but it's just an idea that you can use this and that you can work with that, yeah? If you are have a Unix machine. So cube to raw. Cube to raw, coffee cube, coffee raw file, one frame, as I told you, enter. If you put 2 here, you get it double the size of the raw file. That's the way it works. It just writes it multiple times into this raw file. It's completely useless, but this was useful for to make quick a movie at a certain point in time, to be honest. Okay. So where are we? We did it. Yeah. When you go to this cube to raw stuff, yeah, in this C file here, so that you get this, what's going on here, yeah. In this cube to raw file, we have this line here, line 95. Yeah. So what does it here? It basically scans all the values from the cube file. And as you see, it transforms this using the Arcus-Dungens function. Yeah? You need to know this because the representation of the molecule that we have here, so what happens basically in quantum chemistry world is that you have your atoms, of course, and then you have very high densities around the nuclei, let's say, of the molecule. Yeah? And then you have orbitals that are across different nuclei. So this, okay, which forms the molecular structure, of course. Yeah? The stuff is that these little shells that are focused around an atom, they have way higher probabilities than the ones which are around multiple nuclei, p bonds and whatever that exists, yeah, which share basically orbitals, yeah, and molecular orbitals, yeah. And the story is that that's the one that we are interested in, and so we use this Arcus-Dungens function in order to scale this stuff like that, yeah. So just to get you an idea, what does the Arcus-Dungens function look like? No, arctangent, no, that's what it's called, and that's what it looks like. Do I get an image here? Come on, my little browser, don't be so slow today. This is this arctangent, yeah, and we see, well, this approaches here in the limit minus p half and p half, yeah, and so all the stuff gets scaled, yeah. So if I have very high densities, well, it gets scaled at largest to p half, and here you have a very high contrast, which is interesting because we have a high contrast at the part where we are in with low, let's say low density, and as we go to higher densities, well, they get downscaled using this function, yeah. So if you have here 80, well, it won't be more than pi half, yeah. And as we have this very strong places close to the, let's say, close to the nuclei, where there are these s orbitals which are pretty occupied, I won't see anything else if we don't do this rescaling, and that's why we do this rescaling. Yeah, so a logarithm won't work because of 0 and stuff like that, and this here works better. Yeah, and this here also works because we can use cube files, and you can also generate these cube files for things like like electrostatic potentials with NWChem and stuff like that. And with the Arcus tangent, I have a function that scales me this for correctly also for negative values, which of course here in the density I don't have, but never mind. Yeah. So what we get out of here is let's go back to that. So just if you want to have a different real scale function, you can just change this here. Yeah, of course. So to replace the arctangent here on line 95, it's right now, and in this little at the time as I write this tutorial, to a different function, and it also will work then. Yeah. Whatever I want to do, I do it with the arctangent, and that way I have a nice representation arctangent scaled, if you want to, of our atom. Yeah. Okay. Of our molecule, let's say it like this. Yeah, I have this probability density cloud. Yeah. Okay, yeah, that's the way it works. So anyway, it should be scaled at 1, but you know the way it works. That's the way things are. Yeah. Okay. With this arctangent, going back to our tool here. Where are we? So it did this, and it basically wrote you the limits, and with these limits, you know, so right now you have 256 levels of intensity, and the first level of intensity is 0, and the 256th one is this one, and it's scaled between these two, and that basically gives you the intensity of the electron cloud in this raw file. This arctangent, that's why I get to 1.5 p half. You know it. Yeah. Okay. Perfect. That's the way it works. And we have this raw file right now. Right now, I told you we need this image stack. Yeah. So to get the image stack, I have here a Python file that I will call with Python, because I guess it's not executable if you download this quantum Blender Bliss. Blender Bliss. And here we have this. Where's the file here? What is called Python file here? Raw to image, no? And then I will tell it that I need my coffee raw file, and I want it to 250, because that's what we told him. We have a grid of 250. You have to tell it here, because otherwise this raw to image tool doesn't work. So you have 4 inputs, so your raw file and the voxels here, no? That's the way it works. And if I type enter here, I will get out my stuff. One what? Coffee raw, no such file directory, yeah, because that's in coffee, no? So we do this in coffee, sorry for that, to go into the coffee folder. And then of course, yeah, this still works because this is my home directory. Let's do this here, so up and coffee raw. And let's get our grid definition here. And yeah, because we did here coffee raw, no, you remember that, okay. And enter, and this tool, it takes a bit time, but not that much time either. It reads the raw file. Once it has read the raw file, it will create us all the little images. And with these images, then we can go into Blender and finally visualize our molecule. No, that's what we really want to do. So, okay, let's wait a bit while this is done. Let's see if our NWChem job has finished. Yeah, it has. Yeah, so as I told you, we did this here in the coffee folder. No, or in our, what was it called here? Tutorial. No, tutorial. And you see you have the coffee cube, just as we had it before. You have all these output files. Just to remember, we ran NWChem, something like this. No, it doesn't, not found anymore here, but maybe it was done here. So many panes open here. So you remember we ran NWChem, coffee, NWChem, coffee input, NWChem, and then the output file, no, coffee NWChem out. And you can read this output file and see what it has all done. What is important is that you have your cube with your electron density. Yeah, okay. That's the way it works. So you see it took like maybe half an hour, maybe I don't know, maybe a quarter of an hour. And right now, this little tool here, this little Python script that I've shown you, it writes out our image stack. How cool, no? And as we have this image stack, we can go into Blender and use our shader, which we also have to compile. So I have to compile it. You probably don't. If you download Blender from the website, you can just use the OSL script. I have to compile the OSL script by hand because the way my distribution installs Blender, it doesn't work inside Blender, but that's a different story. But if it doesn't work for you, if you don't have the open shading language compiler, or if you can't install it for your distribution on Gentoo, you can do this. Yeah, I saw that on Ubuntu it's a bit complicated. Just use the Blender internal open shading language by downloading Blender from the Blender website. Yeah? I will compile it here by hand. I will show you how this works, and then we will go back to these images. So that's in this Quantum Blender which we've downloaded, and here this is this OSL file. So this OSL file is basically the shader that generates us the volumetric properties here. Yeah. So I have to compile this with the open shading language compiler, image stack, OSL. That's all I have to do. And I have my shader. I have this OSO file, image wall texture OSO. That's what I need. Yeah, you can do this with the Blender internal stuff just by getting the OSL file. You will see how this will work. So if you have the OSLC compiler, if you have installed open shading language on your system, you can do this that way and generate an OSO file. Otherwise, use the OSL file internally in Blender, and it will work too. Yeah. Especially if you download Blender from the Blender website and don't install it with your distribution package or something like that. Yeah. Okay. Okay. Let's get into Blender maybe. But before we get into Blender, go back to this coffee folder, and I will show you these images. Yeah. So if each, this is basically just an image viewer. You know this. You can also apt-get install FAH if you don't have it. Is a very nice little image viewer. And if I do this here with all my PNG files in this folder, so it starts as this is nicely sorted with these zeros in front, and then the name says this tool here, this little script creates this. So if you see right now the contents of the script after we called this Python script here, just scroll up here. We ran our Python script, we got all these images are in this folder with FAH. I opened all these images, and there basically that's the stack. Yeah. So what do I see here? Yeah. So I get the electron density out. So if I go over here, you see here in the middle the electron density of my nice little coffee molecule, no, in a 250 by 250 cube with voxels that tell me where the electrons are. So this is already this quantum representation. Let's go full screen. It doesn't matter. Can I zoom in here? Let's say zoom. Options, auto zoom. So that's our coffee molecule, no? I hope that the zoom basically gets recorded, but that's the way it is. Yeah, so that's what it looks like. Yeah, without Blender, but we will do this in Blender, and you can imagine in Blender you can turn this in any ways you want, and in any ways you want to do it, and you can do scattering on this, and you can put the molecule into a scene and stuff like that, of course, no, because it's Blender. Yeah. And I will show you how you can run this, how you can render this in Blender. Of course, we won't do the whole render stuff because this is a very poor little machine which won't cope with all that, but you just create a little preview, and you can then imagine that you can create bigger images than these. Yeah. Okay, so enough talk, let's get practical. No? Let's go into Blender. So Blender, I just open it here, Blender 2, my command here is Blender 293. Whatever version you have, it will be probably until right now the same, and it starts up Blender, and I use here select with right, and I use spacebar with search. If you do this in a different way, do it the way you want. That's the way I use Blender. I prefer it that way. I'm used to that. So to select objects here with the right mouse button, and if I hit spacebar, I do search. That's pretty nice, because if I don't know about the tool, I can just hit the spacebar and I get a search window like this. Okay, I also have here, as this is a little laptop, of course, a high resolution screen, but I want to have a bit more space. I guess you still can read it in the YouTube video. So that's the way it is. So I scale my resolution a bit, and if I go here to key map, so if you don't have this write and search stuff, you can get it here in the key map. Yeah, of course you can, according to your convenience, configure this different, but I like it that way, so that if I just hit space, I find the tools that I want. And we already have everything that we need in the scene. So we have the cube, we have a light source, we have a camera, and in the cube basically we will build our image stack as a volume in order to render this molecule. No? Okay, so how do we do that? So we need the cube, so we need the cube, and we need the cube. So it's already selected. Either you select it here, or you select it as I configured it with the right click here. And we have the cube, and here you have this little button here, which looks, I don't know what this is, like a ball. This is basically the material. And okay, just sorry for that. First of all, we have to change our render settings, so we can't use the Eevee stuff for this. We use the cycle stuff. Okay, and we use the open shading language. So click here, open shading language, so that we can use this stuff that we compiled beforehand, or that you compile here inside Blender. Open shading language. I zoomed here with the mouse wheel if you want to know that, but that's the way it is. So open shading language, that's what the important stuff here is, and this also changes the material stuff. So right now you see you have here your material, and we will change this material using nodes. So we will have here, if you right click here on this border here, you can split the window. So we'll do here a horizontal split and create a new window, and this type here basically, or here you can, in this beginning here of the window, you can change the type of window that you have here, and we want to have the shader editor. So once we're in the shader editor, there's something like that, and this here is our material output. And you see here you have volume, and we want to interact with the volume. So first of all, we with X. So I hit X here by forehand. I selected this with my right mouse button, and I deleted the shader here that was here. We don't need this. The shader was just like, when the light ray hits this object, it bounces back, something like that. So let's add a new shader, and I will just use the emission shader, so we can even get rid of the lamp. I do this that way so that it renders faster. So you can use here, of course, these volume absorption and volume scatter, and do this, and get this into the density and connect the volume, and it also will work, and you will get your electron density, and it creates absorption and volume scatter. In this case, I just use the emission shader and emit light where there is volume. That's the way we do it. So we do it like that. We just connect this over here. We keep the cube where it is. I guess you can scale it up. The best to use this is keep the cube as it is, because the shader, it doesn't always do what you want, but if you keep the cube the way it is, it will work. So the cube is on +1, -1 positions with the edges. Okay, add, and then we need this, what is called script, and here we have our so in this Quantum Blender Wiz folder that we downloaded from GitHub, either you use the OSL. If you don't compile it outside, as I showed you with the OSLC compiler, which I have to do for my version of Blender, but so if you download it from the website, you just click here on this OSL, in my case, I have the open shading language installed, so I compiled it outside and I use this OSO file. Yeah, okay, so I have this OSO file. If you clicked on the OSL file, you might have to update the script node here, but you will get the same image here. Yeah, okay. So what does this script basically gives us the correct volume density here that we can put in here into the strength. Yeah, so it's a color. Yeah, okay. So the color, you have this color to black to white converter, but that basically probably overestimates green. Yeah, so the story is like that green is brighter to the eye than red and blue, and that's why this black and white conversion. I wouldn't use this. So I use this separate RGB tool. So because in the file, basically RGB values are all the same. That's the way it's generated with this Python script, and I just use the green channel here in the screen into the strength. Yeah, and so I basically get the density at the right point with that. Yeah? Okay. Next thing that we have to do, let's zoom in here a bit so that you see this nice with the video. There is this I can create this up here, and there's this texture file name. Yeah. And in this texture file name, so here, this here is like this C string, should I say it like 003D, yeah, like you use it in scanf, something like this in C, yeah, in order to get these PNG files that we have here, yeah. And if we look at that back here, yeah, so here you can see me again. Let's go to our folder, our coffee folder. All my terminals are open. Let's open another terminal, okay? So lstd coffee, so that's in my coffee folder here. That's the way I created it. If you put this in another folder, so that's with pvt, I get my current folder. And as you see, this is called image. Then we have here 4 numbers, yeah. So this is O with O leading O. That's why there is this O here. If we go back here, yeah, you have here that's 3 leading. Yeah, we have 4 leading. So we have O, 4 numbers, no 2 here. Yeah, just D, and it's called image. Yeah, okay, because that's the way the script is generated. Image, yeah, leading O's up until to 4 numbers. Dot .png. That's the way it works. Yeah, okay. Dot .png. Okay, and then here I have not // but I have to get it into the right folder. So as I saw with pwd, the right folder, let's copy paste this over here. Doesn't work anyway, I know it. So in my case, that's home Hashka and coffee. No, just make sure we wrote this right. That's the way it is, coffee. And then last thing to do is we have stack low and stack high, and that's basically how many images I have in there. No, and as I have here on my stack here, we have 250, and this counts from 0 to 249. So I have to tell him 0 stack high 249. No. Okay, you also can invert this, then you have an inverted voxel stuff, but I guess, but that's the way it is. So let's just keep this like that, stack low 0 250 with our little script that we have written at that time in 2015, and we opened this in here, and or I don't know where we did the script from, but with this script it basically works. So we get this in there, and we have the volume out here, no? And that's the way it is. So let's toggle the quad view, yeah? Toggle the quad view, and yeah, toggle quad view. So I did this with space, you know, to search, and I type toggle quad view, and you get this little images where you get it in from all sides. You can watch at your scene, and you see your camera and the light. So as I said, we have already emission, so we have the stuff, we let it emit light directly, so we don't need the lamp. So I right click on the lamp, I select the lamp with my right click as I did it with my options here. I type X to delete it, I type enter, the lamp is gone. The stuff will emit light, that's perfect. I also want no light from the world, so I click here on this world button. And here I have this background, so you have a background noise world. We can like color here, and we want the color to be, we want a black, no light world. Yeah, okay. That's the way it is. Okay, that's done. The world is here, the stuff is here in the middle. We have enabled cycle CPU open shading language, and we have created our node. Just to recapitulate, where's my, if I click on the right click on the cube, that's our configuration. So we have our script that generates our stuff. We convert it using the image data into we take just one channel, we put it into the strengths of our shader, and we pipe this to the volume of the object, which is our cube. Okay, let's get the camera closer to the cube. So if I go here, space camera, here I have a camera view now. So then I can see through the camera, and I see that the camera is pretty far from the cube actually, so I want to get very close here. So first of all, I also want to change the scene resolution, so I want to have something like more square-like, so that it fits better. So let's do this 1080 by 1080, and here I can just downsample this by the percentage, so then we have half of the pixels here just there. Let's do maybe for our quick render too, that's 25% of the pixels, very small image, but if you don't want, you can go up here if you have on a high performance machine. Here this is a very low performance machine, and we want to do a very quick render. So I will try to approach the camera here in my 3D view, of course, something like that. I have to go down here a bit. Moving the camera, this is done with the G button, so I just click on it with the right button into G, and can move the camera around like that. Yeah. Okay, G, and then I just click, and then it stays there, and I want to get a bit closer maybe. So really close, you can even get into or always touch the cube, because the molecule inside will be very small anyway. Yeah. Okay, so we have this stack, and right now we can do render. I'm not sure, I guess it uses all my cores. As I record the video, I might do not all threads, so I will just use 2 threads or something like this. So fixed, and let's say 2, so this will be very slow, but that's just to keep this running here. And render image, yeah, you want to use, you don't want to do this, yeah, you want to have all the cores running. And render image, and here's coming up the image, and I hope we already see here a little part of the molecule. What does it tell us? How much time does it need? 2 minutes, something like this. Yeah, maybe we can wait 2 minutes, maybe not. Let's see, what can I do to make this faster here? Of course, as I told you, this is very slow, but that's the way it is. Yeah, so we record, that's the way rendering goes. Yeah, so if you do here more pixels, more 100%, of course this takes way longer, so this is just like 25% of 1080, so it's like 250 by 250 pixels, something like that. Okay, and it renders our molecule. So here we see a very little part of the molecule already. Let's hope we see more very soon. It takes some time. So here you see that the molecule comes up. Yeah, you get the idea. So you see basically the cores, you see this electron density, and of course you could turn then the camera around the cube and have a rotating molecule and stuff like that, or turn the cube, I guess. And you see that that's the way it works, and that's the way you can basically even have animations of this. And here we have our little caffeine molecule, and you can of course color all this stuff, and with the node editor and with all that. I don't want to make a Blender tutorial, I just wanted to show you that how you can get this data into Blender, and how then you can visualize your molecule. And of course we could zoom in here with getting the camera in there and getting a closer view on that. But that's basically it. Yeah. Well, I'm not sure I will wait here. You see that the caffeine molecules is coming up. You get an idea about how all this works. I might show you some images that I've created with this method from, for example, from a propophenon molecule or something like this. So here we have already all of our coffin molecule. We can zoom in here a bit. And that's basically the electron density, and I can of course animate all this as you can do in Blender and create movies with that. And if I have the computational time, or if I render in the cloud, let's not make a Blender tutorial. You get the idea, you've seen how it works. We have our molecule coming up. That's the end of the tutorial. Okay, so let's get this into background here. Yeah, nice to see me again, no, I guess. And I will show you basically what did I wanted to show you, some images, no? So if you go into this quantum blender viz type, if I use here, for example, this propophenon image, if it comes up, so that's what it looks like in full screen, and you see you can create images like this with the internal electronic structure here of this propophenon molecule and the ring and stuff like that. Yeah. Okay, so far so good. You have seen it for this little coffin molecule. I hope this was a nice tutorial that you can render molecules the way they are intended to look like, or I mean look like. Yeah, what does a molecule look like, to be honest? If you interact with light with an electron, it will probably fly away. So yeah, let's keep it here. Here I showed you how to visualize the electron density, or how to visualize molecules on a quantum mechanical level. I hope you found this tutorial fun, and let's stop it here. Thanks so much. Bye bye.